Hi guys, in this video we will continue our look at imines or Schiff bases. Lots of applications of imines. We saw some specialized imines such as hydrazones, oximes. We saw a 2,4-DNP test, which is formation of the 2,4-dinitrophenylhydrazone. Which always forms a yellow-orange precipitate. And if your aldehyde or ketone is a liquid, the formation of that precipitate is an indication of an aldehyde or ketone. The 2,4-DNP derivatives are also used as solid derivatives, so maybe you can take a melting point of that derivative. At this point, we are at the Wolff-Kishner reduction. This is a reaction we saw back during when we were looking at aromatic chemistry, and the acylation. This could be formed by a Friedel-Crafts acylation reaction, and then we reduced off the oxygen to give the alkyl group. And we had three different ways to do that, and one of the ways was the Wolff-Kishner reduction. And now we can look at this mechanism. And the first step in the mechanism is formation of the hydrazone by reacting with hydrazine. Okay? Now, by the way, these sometimes are shown with an acid catalyst, but the acid catalyst is not always needed, particularly for hydrazones and oximes, because the imine carbon-nitrogen double bond is conjugated with a lone pair. And in these cases, the double bond is also conjugated with the benzene ring. So, we do not have an acid catalyst here. We are under basic conditions. But the first reaction is formation of the hydrazone. Now, I'm not going to show the full mechanism here. All right? We've already looked at the mechanism for forming a imine, except here we used acid catalyst. Over here, there is no acid catalyst. But here's your hydrazone that would form. From there, the hydroxide becomes important, and we can pick up the mechanism here. And it's important to realize that we are going to form nitrogen gas, N triple bond N, and we want to get H's on that carbon there. And the first step from the hydrazone is deprotonation of the NH here. Trying to find a smaller N. Here we go. And so hydroxide acts as a base, takes an H, electrons stay behind, and that will give that anion plus water. But this is resonance stabilized, and these electrons can move in here, and these electrons out onto carbon. And we now have double bond between nitrogens. That nitrogen is now neutral, And now we have a lone pair on carbon, and the carbon is minus. That's just a resonance structure. At this point, we can protonate the carbanion with water serving as the proton source, and that gives 1 H on that carbon. Ultimately, we're looking to get 2 there. All right. Now each step here is probably reversible. I mean, if we had this, could we deprotonate this? Get back here? Yes, back to a resonance stabilized, okay, anion. And we could, this nitrogen could take an H from water, we could get back here, okay, reversible. But if we keep going forward, all right, we made hydroxide again right here. And the hydroxide we will see, I believe, is catalyst. Let's see. Minus. Now we take the other H. Electrons behind. Double bond in. Now we have a nitrogen anion plus water again. Now at this point we're almost repeating what we did the first time, except here it's not resonance. These electrons are going to move in here, make triple bond between nitrogen, and this carbon here is going to be kicked off as a leaving group. All right, now this step is a little bit difficult here. That's a plain carbon. In this case it is resonance stabilized. But you do not have to have a benzene ring here or resonance to do this. But you do typically need high heat. And usually Wolff-Kishner requires like 200, 300 degrees. But that will give that plus nitrogen, triple bond nitrogen. And there is our nitrogen gas we said we would form. And now this carbanion takes an H from water, leave electrons behind, and we will get our final product. Now 2 H's on that carbon. All right, I'm not going to draw them in. And we do remake hydroxide. And so it was catalyst. But it's the catalyst for this part, all right? Formation of the hydrazone could be acid catalyzed. There is no acid here, so there's no catalyst for that. The hydroxide is the catalyst from that point. Ultimately, the Wolff-Kishner mechanism is pretty straightforward. It's just acid-base chemistry. Take off H. It's almost like an enol or enolization, tautomerization. Take off H, do resonance, put it back on. But we put it back on carbon. Take off H. This is not resonance though because we're breaking a sigma bond. And then the carbanion that gets expelled here, or the leaving group here. All right, anytime you make a pi bond, kick off a leaving group. All right, even though it's kind of a plain carbon, we can do this. It does require some heat, and then that picks up an H from water, and now you have two H's on the carbon. All right, that's the Wolff-Kishner mechanism. I promised you back when we were looking at aromatics that we would do that mechanism later, and now we've done it. Okay, next, D, Strecker amino acid synthesis. It's also going to involve an imine. And we have potassium cyanide's a solid, ammonium chloride's a solid. And this is a way to make amino acids, alpha amino acids. Okay, alpha amino. The first carbon coming off the carbonyl is the alpha. Okay, and this is you should probably see this in biochemistry. This involves reacting an aldehyde or ketone, but usually an aldehyde, because usually these alpha amino acids are going to have an H on that carbon here, with ammonia, and that will give the imine. All right, now how do we get ammonia? Because we have ammonium chloride and we have potassium or sodium cyanide. But these can react, and this cyanide can take an H, and we can actually get an equilibrium where we have HCN plus ammonia. And then potassium chloride. So, because cyanide is slightly basic, it can deprotonate the ammonium, and we can have ammonia. Reaction of the aldehyde or ketone with ammonia gives the imine, right? Right back over here. Again, acid catalyst is not always needed. Now from there, if you have cyanide, all right, and we just do, now how do we get cyanide if we have HCN? Well, the imine, why don't we protonate it first? We can do it either way. It all depends on how strong of an acid is HCN. It's not that strong of an acid. We can do an addition first. That would give all right, that there. Don't know if I like this, because now we're just going to show an H+. But if you got H+, you should have reacted it over here. But essentially, if we have H+, then we can protonate that nitrogen, and that would give us that product there. From the imine, it's a lot like reacting an aldehyde or ketone with HCN to make a cyanohydrin. Now instead of that reacting, we could react this with H+, If we consider this, an acid, H plus and Cn minus, and we can protonate that. Then if the cyanide adds up, positive charge, electrons up, then that gives that way. Sort of all depends on if HCN is acidic enough to protonate. I think that's a better way to go. It's sort of vague a little bit. But ultimately, if we have an imine here and then we react with HCN, we can get this intermediate here. Now, it really doesn't have a name. If that was an OH, it'd be a cyanohydrin. But this cyano-substituted amine, or alpha-cyanoamine, the cyano group can then be hydrolyzed. And if we do that, we get an alpha amino acid. Now the hydrolysis of the nitrile group, of course, we saw during test 3, but we also saw it right back over here. Okay. The only difference is instead of an OH, we have an amino group. And the amino group came from HCN adding to not an aldehyde ketone, but an imine. All right. So for homework, show a Strecker amino acid synthesis of leucine. All right, just working backwards. Okay. And you will begin with an aldehyde, right? Didn't we begin with an aldehyde here? But work backwards, okay? That is before the last step is hydrolysis of a cyano group, and so going to get that there. And then keep going backwards. Okay, retrosynthetic analysis. Until you get back to the aldehyde. Okay, E. Continuing under imines. Lots of applications of imines. Reductive amination. All right. Very important reaction. Probably one of the top 10 or top 20 reactions in organic chemistry. You can make an imine, but one thing you can do with imines is you can reduce the double bond. And if you do that, you get an amine or amine. Okay? Now I've turned the carbon nitrogen this way instead of up. Okay? But all we've done here is reduce the CN double bond to a single bond. And the nitrogen gets an H and the carbon gets an H. Okay? Now this can be done with hydrogenation. All right, just like an alkene can be converted to an alkane, we can also convert an imine to a amine. And since nitrogen, we also always show H's, right? All right. We can do this with hydrogenation, palladium, platinum, nickel, sort of your standard precious metal catalyst for hydrogenation. But we can also reduce this with sodium borohydride or LAH. And that's because the imine is a polar bond. and the carbon is partial positive. And H minus will add to that carbon, okay? And now we have two H's on that carbon. In this case, it doesn't have to be an H to be an imine. And that's going to give nitrogen anion, yeah? And we need a proton source. That can either be a workup, but with sodium borohydride, we can use a protic solvent such as ethanol, okay? And if we do this reaction in ethanol, it will serve as the proton source. Phenyl CH2 NHR, all right? And I just drew a traditional zigzag, and yes, that carbon has two H's now. And you will make the ethoxide, and so at the end your reaction will be basic, okay? But then you can isolate your product somehow. So reduction of the imine to the amine, all right. So imines can be reduced like this. Now, let's put it in context here. What if we combine all this together? And what if we have an aldehyde ketone with an amine and at the same time hydrogen with a precious metal catalyst? All right, that would give the amine product, amine, all combined. Because first step here is reaction of the aldehyde with methylamine, and that will give, no, not aromatic, not aromatic, okay, that's the cyclohexane. Imine, I'll put that in brackets because we're not going to isolate it. If we have hydrogen there, the carbon-nitrogen double bond will be hydrogenated and you will get the amine product. Now I fear that some of you are not seeing this because I've done zigzag. Oh, okay. I could draw the product like this. Instead of a double bond, it's now single. And there's an extra H added to carbon and nitrogen. The extra H on nitrogen we're going to draw in, or the new H on nitrogen. The new H on carbon we're not. Carbon has one H there, two H's here, okay? But these two are the same exact thing. All right, same. And this is called a reductive amination, okay? Reductive amination of an aldehyde or ketone. Start with an aldehyde or ketone. All right. Now, let's try another one. Methylamine again, but let's include sodium borohydride instead of hydrogen. And with methylamine, we're looking to make the imine. All right. But that would not be isolated. And then the sodium borohydride. And let's show some ethanol because we need a proton source to put the proton on. Would reduce the double bond to give the amine. The problem is this will not work the same as above because sodium borohydride will reduce the starting ketone. All right. It's not going to wait until you get the imine formed and then reduce only the imine. Now up here, hydrogenation typically will not reduce an aldehyde or ketone unless it's benzylic. So that'll work. But this will not. Has nothing to do with me changing the aldehyde or ketone. It doesn't work because the sodium borohydride will reduce the carbonyl compound. All right. But never fear. We do have a reagent that we can use here, and that is sodium cyanoborohydride. And so we get the imine and the sodium cyanoborohydride will only reduce the imine. It will not reduce the aldehyde or ketone. Now this is instead of one of the H's of sodium borohydride is replaced with a cyano group. So we have B, H, okay, and then the cyano group. The boron is still minus, okay, then you have the sodium. But because the cyano group is electron withdrawing, it's not as strong of a hydride source. It's all right, it's weaker. And it turns out it will only reduce the imine. And because of that, we can include both the amine and the reducing agent together. And we have a nice reductive amination of an aldehyde or ketone. Now you have to envision this. In the reductive amination sequence, we first make the imine. This becomes a nitrogen instead of oxygen. But then we know that we can reduce that double bond and we can have an amine. All right. So here's some here to predict products for homework. The third one, it's only one molecule here. All right. It's going to be a intramolecular reaction. All right. So sodium cyanoborohydride, its claim to fame is for use in a reductive amination sequence reaction of an aldehyde or ketone with an amine, including the reducing agent, and the imine gets reduced to the amine. All right, some to try for practice there. Now, this also brings us to synthesis of methamphetamine. All right. This is methamphetamine here, fairly small molecule. Potent psychological effects. By the way, if you take the methyl off of methamphetamine, you have just amphetamine. If you add an OH to methamphetamine, here at the benzylic carbon you have Sudafed. Now you can actually do sort of some garage chemistry and remove the OH group from Sudafed and make methamphetamine. And that's what some illegal amateur chemists try to do. Go to the drugstore, stock up on Sudafed, and then do this chemistry in their meth lab. Yeah. That's why nowadays you can no longer buy cases of Sudafed at the drugstore. They will only sell you one box, and you have to show identification. Big difference is when you remove the polar OH group, methamphetamine, being less polar, gets into the brain more and has a more pronounced CNS effect. Amphetamine, and by the way, if you put an OH on amphetamine, you have a compound known as phenylpropanolamine. It's a stimulant actually used in some diet pills and in so-called no-dose pills. It'll keep you awake. All right. You know, it's a legal upper, where amphetamine is illegal. Sometimes used as prescription. Adderall is actually amphetamine. But methamphetamine, with the methyl group, it's less polar, more lipophilic than amphetamine. Anyway, these are some molecules that may be of interest. So let's provide two different syntheses of meth, with both employing or using a reductive amination approach. All right. Two different reductive amination approaches to give methamphetamine. All right, we just covered reductive amination. All right, what are the main components? All right, aldehyde or ketone and an amine. All right. See if you can do that there. Okay. We'll end this here. In the next video, we'll finish up this looking at applications of imines by looking at some drug metabolism, a little bit of biological or biochemical applications. We'll finish that up. Then we'll move on and we'll look at the Wittig reaction. All right. And that will finish up this handout, and we'll be then ready to move into our next handout, which is most likely the alpha carbonyl chemistry.